SolidWorks is proud to be a sponsor and global CAD provider for the F1 in Schools program. Students involved with the event receive SolidWorks software to design, simulate, document, and present their projects before ever building them. Using SolidWorks' powerful yet easy-to-learn 3D CAD tools, students will design their own unique cars, and they will produce professional quality detailed drawings. But most importantly, because performance is crucial in this challenge, students will virtually wind tunnel test their designs in SolidWorks. By simulating the flow of air around their models at racing speeds, students can make important design decisions before they ever begin building their cars. In this example, we're measuring the aerodynamic effects resulting from changing the angle of attack of the spoilers. Now let's take a look at how a student would create a model in SolidWorks. First, they begin by sketching two-dimensional geometry on the screen. There are many sketching tools, including lines, circles, splines, rectangles, and others. Once this geometry is created, the user can then assign dimensions that will control the model, then transform it into a 3D solid by simply dragging it to the correct thickness. Using these same sketch tools, one can also remove material. Here, we'll create some cutouts in the back of our block. Since its initial release in 1995, SolidWorks has set the standard for usability in 3D CAD design. Students will quickly master the intuitive interface and be able to concentrate fully on the creative and analytical aspects of their designs rather than on the complex menus and commands. Notice how the tools we need are always available right in the main graphics area, and because of this, we haven't needed to access a single menu or even the main toolbar at the top of the screen. Once we've created our sketch, we can then tell SolidWorks how far to cut into the model. First, we'll extend the bottom slot so it runs all the way through the model. Then we'll drag the CO2 canister hole to a depth of 52 millimeters. So now we have a perfectly sized block to begin our design, but what is its mass? To find out, we must assign the proper material to the part, in this case balsa wood, and with the click of a button, we can display the mass as well as the volume, surface area, and moments of inertia. Knowing that this car will be symmetrical, before I continue with the design, I'll cut it in half right now. I can always mirror the other half when I'm done. We begin by shaping the car by sketching a side profile and cutting away any material above that profile. We'll repeat this procedure for the rear as well as the top. And with only these first 3 cuts, we begin to recognize the shape of our F1 in Schools car. SolidWorks also gives us advanced lofting and surfacing tools to turn a basic design into something more visually appealing. We can use lofting to create shapes that would not be possible to make using a single two-dimensional sketch. To complete the cockpit of the car, we'll also use a cut and some fillets to blend all the design features together smoothly. And with a comprehensive tool set for creating advanced freeform surfaces, SolidWorks makes even designing the complex shape of the side pod very easy. As we reveal the final features for this car model, notice how every step of our design process is organized on the left side of the screen in our patented Feature Manager. And with SolidWorks, we can easily change any feature of our model as our design evolves. For example, to change the angle of attack on our rear wing, we simply need to click on the wing and drag the angle to a new value. We can use the graphical preview as a guide, or we can type in an exact value. In SolidWorks, we can even store multiple configurations of our models using these different values so that we can easily compare our designs without creating more model files. The next step is to put this car together. We can model all of the components found in the F1 in Schools challenge and store them in a component library. Then we simply drag the components from our library to our car assembly and use the make command to tell SolidWorks how they need to fit together. As we step through this process, notice once again how SolidWorks puts all of the tools we need right on the model. As we pick on the geometric features of each component, SolidWorks predicts how we want to relate the components, but it also gives us the freedom to override its choice. In this way, we can switch the alignment, add clearances, specify ranges of motion, and far more. Next, we step through a wizard to define the conditions and goals for our flow simulation. After less than 15 minutes on a laptop computer, we can produce static and animated plots that graphically depict pressure, temperature, velocity, and more. By studying these plots, we can gain insight into how our designs work and make better decisions about how to improve them. For example, in this pressure plot, the large red area signals that the front wheel is a major contributor to drag, and that we should redesign our front spoiler to address this problem. Using our configurations, we can also compare simulation results for multiple versions of our car and even export the calculated design goal data into Microsoft Excel for side-by-side comparisons. The goals export generates useful tables and graphs inside of Excel that are perfect for design reports or further analysis. F1 in Schools participants will also appreciate how effortlessly they can create high-quality renderings and animations of their models. Without ever leaving SolidWorks, they can experiment with different surface finishes, textures and decals, camera angles and environments. They'll get excellent results in real time and photo quality results in seconds. By using SolidWorks to complete your F1 in Schools design, you can truly embrace modern engineering processes without sacrificing usability or fun.